All right, today we're going to continue our discussion of the normal distribution, and specifically we're going to be looking at some applied word problems today. So hopefully you're ready for that. I know you guys all love word problems so much. So to get us off on the right foot though, actually I'm going to show you some memes on the normal distribution. I don't know if you've ever seen any of these, but I just Googled them, and turns out there's actually a lot of good memes for the normal distribution. So I'll show you some of these. We've got our normal distribution versus paranormal distribution. Here is a good pickup line for you here. Your beauty skews the normal distribution. All right. And how does one represent the mean of the normal distribution? Mu. Of course, that is the letter for the mean, right? Mu. If we get that one. Here we go. Does this make me look normal? Just got the normal distribution hat. This one might take a little imagination, but I didn't quite understand this when I first looked at it. 4 pictures of the normal distribution that'll make you say that's DJ Khaled. I think that's how you say the name, right? Not the normal distribution. So it took me a second to kind of get this, but I think what they're going for here is if you kind of trace his outline, if I can get, so there we go. Trace his outline. I guess it kind of looks like the normal distribution here. All right. A little bit off. Sorry, I drew that one poorly. So there's a normal distribution, I guess. So his outline, I guess, is approximately normal. I don't know. It's kind of entertaining, I guess. Right. And here is a Star Wars one for any Star Wars fans. Help us normal distribution curve. You are only hope. Of course, that is Princess Leia from Star Wars: A New Hope. So there's a lot of good ones. Hopefully found at least one of those entertaining. All right. So we're going to start by just actually doing something we did at the last video, and that is talking about how you find the area under a normal distribution. Now, in the last video, we didn't actually have to do this first step. We didn't have to calculate the z-score because they gave us the z-score, and then we just looked up the table value. However, in these word problems, it's not going to give you a z-score. You're going to actually have to do this calculation. So it's really putting the last 2 videos together. Calculating the z-score was 2 videos ago. Last video was then looking at the table and making some judgment about that. So first thing we might want to do is just a refresher on how do you calculate the z-score. So the z-score is the observed value x minus mu, the mean, over sigma. X minus mu over sigma. So that is going to be important. Very easy calculation. Next, we're going to look up the corresponding table value. So we had a couple different options for that table value, either in your textbook, digital textbook, or that document that I gave you, which I'll show you how to get that as well. If we're looking for the area left of the z-score, generally it's a less than problem. We're just going to take whatever that table value is. If we're looking for the area to the right of the z-score, generally a greater than or equal to 1. It's going to be 1 minus the table value. And if it's an area between 2 z-scores, we're going to do the larger table value minus the smaller table value. Because remember, these table values show you the area to the left of that z-score. All right, so let's get to it here. So our first applied problem here. This is most graduate schools of business require applicants for admission to take the Graduate Management Admissions Council, or the GMAT, examination. Scores on the GMAT are roughly normally distributed with a mean of 527 and a standard deviation of 112. So what's the probability of an individual scoring below a 500 on the GMAT? All right. So notice we've got our 3 things that we need for a z-score. We've got a mu, we've got a sigma, and we got an x, right? So first thing we want to do is get our z. 500 minus 527 divided by our standard deviation of 112. You do need to make sure when you're doing these problems that you're writing this workout. Just don't write what z is. I do want you to show how you made this calculation. And here we get negative 0.241. Sufficient? All right, so we got our z-score. The next thing we need to do is look up a table value, and we need to figure out if we're going to be looking at less than, greater than, or between. Now, the keyword in this one is below a 500. So that's going to speak to less than, right? which just means we want just to the left or the table value. That's all we need is the table value. So I'm going to go, actually forgot to pull up our table value here, table. I guess this would be a good place to show you. If you forgot where the tables are, just go to Providence Stats page. And I'll put this in this week's as well, this next week's here. But we're going to be looking at the table of values. Here, standard normal table. All right. So our standard normal table, and we, again, want to look for negative 0.241. So how we find that? Negative 0.2. It's negative 0.2, and then it's 0, 1, 2, 3, 4. So it's going to be this one here. Negative 0.24. It's going to be good. So that's 0.40517. All right. Or we could say approximately 40.5%. So you would say 40.5% of individuals who take the GMAT get below 500. Okay, so hopefully that one made sense. Next one was the probability of an individual scoring above a 600. Okay, so we got the same mu, same standard deviation. X value is now 600. So Z is 600 minus our mean 527 over 112. Just punch that into our calculator. And we get 0.6517. Now, before we go looking up our table values, let's think about what we're going to be doing. It's the probability of above, so that's going to be greater than or to the right. So we want to do 1 minus our table value, right? 1 minus table value. So 1 minus, and then let's look up the table value of 0.65. It's going to be on the second page. 0.65 is going to be right here. Right. So again, you just find the first decimal place on the left side and then trace it over to the column that matches up. So 0.74215. 1 minus 0.74215. So we'll type that in. And we get 0.2578, or I guess you could say 25.8% chance. So maybe a particular school has, you have to get at least a 600 on the GMAT in order to get into a specific business school. Well, the average person would have like a 25% chance of getting above a 600. Okay. Let's go and look at our next example. So this one, sorry, we'll go into this one. The average number of acres burned by forest fires and range fires in Moore County, New Mexico, is approximately 4,300 acres per year. So every year they expect about 4,300 acres to be burned, just based off of past years. Standard deviation is 750 acres. The normal distribution of the number of acres burned is approximately normal. So this follows normal distribution, meaning if they've collected all this data, you plot it, and it follows the normal distribution. So what is the probability of that between 2,500 and 4,200 acres will be burned in any given year? Okay, so this is a between, which means we're going to need 2 Z values, right? 2 Z scores, and then we're going to do the larger table value minus the smaller. So our first Z, call this Z sub 1, is going to be 2,500 minus our mean right here, 4,300, over our standard deviation right here, sigma, of 750. And then our second Z score is going to be that 4,200 minus 4,300 over 750. So we'll take a sec and do those calculations. The first one we get negative 2.4. And the second one, we get negative 0.133. With these z-scores, if you ever get like a crazy number, crazy meaning like 10, generally means you probably did something wrong in your calculations. Anything outside of like a 3 or -3 is generally probably made a mistake, or the value is such a big outlier that it would be like a 0% chance. So just a heads up there. All right, so let's go ahead and look these up. And again, we want to do not necessarily the larger z-score, we want to do the larger table value. Remember, it's larger table value minus smaller. So it's not going to be the table value of z1. Actually, that's going to be our smaller one. Even though it seems like a bigger number, it is actually a smaller number as well because it's negative, so it is smaller. But again, we always want our larger table value minus our smaller table value. So I'm going to look up the -0.13 first. -0.13. Sorry, 0.13. 0.13 should be 0, 1, 2, 3 right here. So 0.44828. And then minus our smaller table value of -0.24. And I guess that was 0.24 is 0. Yeah, just 0.24 is 0. There's nothing there, so we want to look up -0.24 is 0, which is 0.00820. Let's do the math on that one. And we get 0.44008, so about a 44.0% chance of the number of wildfires being between 2,500 to 4,200. Right? So our next applied problem says that the county has budgeted enough money to firefight at least 6,000 acres. So they want to make sure they got plenty of money in the budget. So they're going to say, we're going to go above and beyond, make sure we have enough money in our budget. So if it's a abnormally large, active year, we've got enough money to cover 6,000 acres. So the question is, how likely is it that there could be a budget shortfall? So how likely is it that they won't have enough money to fight fires? If they're budgeting for 6,000, but how likely is it that that would be a shortfall, meaning they don't have enough money to cover that? Okay, so let's start by just getting our z-score. Obviously, this is going to be our x value. So it's going to be 6,000 minus 4,300 over 750. And that's 2.266. All right. Now the next question is, what table value are we looking for? All right. Now, if there's a budget shortfall, okay, that means there's not enough money. That means the number of acres burned is more than they budgeted, right? So it's more than 6,000 acres. That's what it's saying. How likely is it that there's going to be more than 6,000 acres burned? Because that's the scenario where they'd have a shortfall. So we're talking about a more than, that means we want the area to the right. So it's going to be 1 minus table value. So let's look at the table value for 2.26. .26 going to be here. 0.98809. 1 minus 0.98809. All right. So that's going to be a really small percentage, right? 0.0119. So that's like a 1.2% chance, basically, if we move it 2 places, right? So very small chance that we'll have a budget shortfall. There is, there's still a chance. If you wanted to make it so there was no chance, then they might want to budget for more like 6,500 or 7,000. But they probably think that, this amount of risk is fine. We only got a 1% chance that we're not going to have enough money. So we're good with that risk. I did think it was interesting, just this idea of forest fire. So I looked up just on Wikipedia, like how many acres is normal for a forest fire. And I looked up California because that's where you generally hear about them. And if you just look, this is from the year 2020. Look at the number of wildfires here, and particularly like the size of some of these things. They're just enormous. So like this one is 396,000 acres were burned. This one's at over 1 million acres, 8,000, 363,000, 19,000, 318,000. It's just amazing how many wildfires there are and how many acres are burned every year in California. I mean, this list is just, it's huge, the number of acres burned in California, which I think in Ohio we kind of lose sight of that because wildfires aren't really a thing around here. And most of these are actually lightning sparked, which kind of tells you that's actually kind of nature just doing its thing, right? Wildfires are a natural part of nature. They're obviously not good if they're near homes and stuff, but it's nature's sort of way of like regenerating, I guess, right? Burn forests down and then new forests grow. And so it's kind of interesting to see that. At least I was fascinated by it. Especially if you're an FMS, maybe you've got a little experience with that, or maybe you've looked into that before. Or maybe you want to move out west and become a firefighter for wildfires. All right, last one here. The length of human pregnancies from conception to birth approximates a normal distribution with a mean of 266 days and a standard deviation of 16 days. So what this is saying is on average, from conception to birth, babies basically take 266 days to grow inside the womb. They're normally born after 266 days with a standard deviation of 16 days. Obviously, every baby isn't born on the due date. They're born within some sort of range within standard deviation here, again, is 16 days. So you could actually say, like, using our empirical rule stuff, right? Remember from the empirical rule, it was like 68% are born within one standard deviation. So you could actually say 68% within 250 to 282, right, days. So it would be, kind of unusual to be born outside of that or before that. Then you go further, right? 2 standard deviations, 95%, right? If we were to kind of continue this deal, 95% would be within, subtract or 16 there would be 234 to what? 298. All right. So kind of interesting, right? My wife with our first 2 kids, she's always been within like 3 days or so, never on the due date, but within like 3 days. So we'll definitely fit within that window there. All right. So first question, what proportion of pregnancies will last between 240 to 270 days? So that represents 8 months to 9 months. So you can see this 266 days is a little bit short of 9 months on average, right? Generally we say 9 months. So it's just right around 9 months. But this here question would say, like, what's the probability that's going to be between 8 and 9 months? Okay, so we're going to need 2 z-scores. And again, we're going to do our big table value minus our small one. So our z1 is going to be 270 minus our mean of 266. 70 over our standard deviation of 16. So that one's actually kind of easy. It's going to be 4, right, on top, over 16 to 1/4 or 0.25. Don't even need a calculator for that one. Z2 is going to be, actually I already did the big one first, so, oh well. 240 minus 266 over 16. That's going to be negative 26 over 16. Well, I do the calculator with that one just to be sure. All right, and that we get negative 1.625. So those are our 2 z-scores. So again, we want to do the bigger table value minus the smaller, which is going to be the table value of 0.25 first. So I'll look that up. 0.25 is right here. 0.59871. Minus our smaller one of negative 1.62. Negative 1.62 is going to be right here. 0.05262. right, let's go and do that. And we get 0.5460. So about 54.6% of pregnancies or birth to conception last between 8 and 9 months, over half of them. All right, so last one I wanted to kind of just take a look at a rare case on this one, just made this one up. What is the probability of a pregnancy lasting at least 10 months? So at least 10 months, that's applying really 10 or more, right? So in other words, greater than 300 days, greater than or equal to 300 days. Now, in reality, today's world, they don't really let pregnancies go this long. If you went that long, they would just induce you and have a C-section. Back in the day, I don't know. I think they just kind of had to let them go. But we've got modern medicine that won't let you probably go past 30 days past your due date. I wouldn't imagine any modern medicine would allow you to do that. Again, they would induce the baby and probably have a C-section. But let's just consider a scenario. Is it possible for a baby to be in there basically more than 300 days? So let's go ahead and look at it. I don't know what the result is here, so we'll see. So our Z-score is going to be 300 minus 270 over 16. So we get 30 over 16. We get a little under 2. So 1.875 is our Z-score. We're asking greater than. So greater than is going to be to the right. So it's going to be 1 minus our table value. So 1 minus the Z-score of 1.87. And that's going to be over here. 0.96926. 0.96926. All right. So 0.0307. So basically about a 3% chance. Or you could say a 3.1, I guess you could say. So very slim. It's bigger than I thought, actually. A 3% or more chance that it could be beyond 300 days. But again, I don't think they really let women go this long anymore. I think they generally would induce labor before then. So I don't know. Maybe one of the clinical care students, you can look that up. Whatever. All right. Hopefully you found at least some of those kind of interesting. The good thing about these applied problems is I feel like they're a little more interesting rather than just straight computations. Take a little more thinking, which you might not like, but it is good for you. So if you are struggling with the problems, make sure you do reach out to me. All right. See you guys later.